Okay. So thank you for the introduction. My name is Konrad Norowski from the Institute of Physics, Polish Academy of Science, and my PhD advisor is Dr. Maciej Zgirski, who couldn't be here. So I will assist in conveying our measurements regarding the fastest thermometer in the nanoworld. So to start, I would like to remind what is thermodynamics in a very general overview. So this is the discipline that investigates heat flows between some bodies or systems, and this heat flow is arising from the difference in temperature between them. So we have some systems that are linked with some thermal interaction between them, and in order to observe this heat flow, we need to have some temperature difference or temperature gradient. And to give you some simple example, I draw here a system consisting some subsystem with heat capacity, call it CV, and the reservoir with the infinite capacity, so you cannot change the temperature of this reservoir. They are linked by some thermal interaction that provides the possibility of cooling or heating our small subsystem. So we can, in the simplest case, we can linearize this heat flow of this thermal link, and we obtain the following differential equation that governs the temporal evolution of the temperature in the system. And it follows that we should expect the exponential decay in such a system, where the decay rate of the temperature is given by heat capacity divided by the thermal link or thermal conductance between the subsystem and the reservoir. And I will be talking about the nanoscale samples, measurement in the nanoscale. So the expected lifetimes or decay rates will be relatively fast, of the order of nanoseconds or microseconds. There are many, there is a variety kind of heat flows at nanoscale. So I drew here electron system that is connected to phonons and to substrate. So the issue here is that we have some conducting example that was evaporated on a silicon substrate, and the substrate is mounted on sorry, the silicon. Okay, we have phonons of silicon and phonons of substrate as well. So we can have many kind of heat flows in such a system. For example, we can observe diffusion of electrons from one place to the another. These electrons can absorb photon radiation. They can emit it as well. They can also emit or absorb phonons from the film or from the substrate. And the problem with the heat flows at nanoscale, as I said a moment ago, they are relatively fast. So to this day, all of these heat flows were measured mostly in steady state. And in order to observe thermal transients, we would like to measure in this nanosecond regime, but we need a fast thermometer. So to reiterate, we can, for example, without measuring the dynamics, we can measure the heat thermal conductance. So if you happen to heat your subsystem with some steady rate, at some point you will obtain some steady state temperature. So you can from the measured overheating, you can infer the thermal conductance. So this is standard steady state measurement, and this kind of measurements have been done for a very long time. But the problem with this is the fact that it does not include heat capacity at all. I mean, it influences the rate of obtain how fast we will obtain the steady state, but other than that, heat capacity is not included. So this steady state measurements cannot measure dynamics, which is a shame, because as some big figures in the field of nanoscale measurements have said, thermodynamic studies is somewhat lacked with respect to electrical and magnetic investigations, and this is mainly due to the fact that there were no actually fast and robust thermometers to this day. And for example, Jukka Pekola from Finland said that if we would have fast thermometry, that would be very nice, because that would expand the variety of the phenomena to be explored. So we can we would be able then to trace fast thermal processes, for example, energy relaxation rates, non-equilibrium conditions, and the small fluctuations in the nanoscale systems. So to introduce the notion of the thermometry, they are mainly divided on two kinds. So we have direct temperature determination, which is the foundation of the primary thermometers, and most thermometers that are actually in use is based on indirect temperature determination. So in primary thermometers, we are kind of lucky because the physics itself give us the temperature in a very simple way. So for example, I draw here the transport measurement in a Coulomb blockade regime, and so the conductance in this case has this dip, and the width of this dip, which is important, is directly related to the temperature. So if you measure the width of this transport measurement property, you immediately have the temperature, given that you know the physical constant. But this is often not the case, and most of the thermometers that are actually used, for example, in the cryostats, need calibration. So the calibration is done in the following way. You must know the temperature, and then you measure some temperature-dependent property of your thermometer. You sweep this temperature and measure this thermometric function, and then you can take your thermometer, place it somewhere else, and then by measuring this thermometric function, you can obtain the value of the temperature in some new system. So now I would like to show the previous state-of-the-art thermometry when it comes to the speed of this temperature obtaining, or bandwidth, if you will. So this is on-chip thermometry using RF frequencies. So in general, you have some radio frequency compatible system. For example, it can be superconducting resonator, and you perform simple refractometry study. So you send some signal on your thermometer. The signal is being reflected due to the impedance mismatch, and the basis of thermometry in this case is because this reflection coefficient can be temperature dependent. So if I recall correctly, the bandwidth of such methods is of the order of 300 nanoseconds. So it could, in theory, catches the slower thermal processes, but this is not enough for tracking the faster ones. So now in this place we start to present our thermometer, which is a superconducting nanobridge. This is relatively simple to produce structure because this is just aluminum nanowire with the nanobridge embedded inside it, in the middle of it. So this bridge has a property that the transport properties of such a structure is strongly temperature dependent, and this is the foundation for the thermometry using such a structure. Now I would like to say things about the transport properties that is the foundation for this thermometry a little more. So we have an experimental setup for just measuring IV characteristic of our sample, that is this X over here. So we just force the current through our system, through our sample, and we measure voltage drop across the sample. And if we do that, we will obtain such a thing. So we have superconducting branch that is in the middle of the graph. So we can force some current through our sample without observing any voltage drop. So this is state of the zero resistance. And upon exceeding some current, we transit from the superconducting state of this vertical normal superconducting branch to the normal state that is characterized by slope with non-zero voltage drop or non-zero resistance. And now where our thermometry is hidden is near this transition. So if you remember from the theory of the phase transition, if you are near it, if you are near the transition, the fluctuations, either thermal or quantum origin, become important. So here we have such a situation that this transition can become stochastic. So it has a probabilistic nature, and we would like to measure this switching probability. And by switching, I mean just a transition between superconducting and normal state. So what we actually do is we test switching of our superconducting nanobridge with current pulses. If we test it with some low current value, the junction never switches, so we observe no voltage response, there are no voltage drops. If we test our sample with high current, all pulses result in the switching, and in between there is a transition region where some pulses produce switching and some pulses not, despite the fact they are all of the same height. So this is the probabilistic or stochastic nature of this switching. Now by sweeping the value of the current of these pulses, we obtain such relationship between switching probability and the current, and it's called an S-curve from the S shape or from the fact that we measure switching. Now the thing is that you can tune the probability of the switching by a current. So let's just take the probability of 0.5, and the probability of 0.5 resembles a very simple statistic experiment, which is a coin flip. So you can obtain heads or tails. And our bridge is indeed some kind of an electrical coin with the probability that can be tuned by the current. And we can ask, is it actually a good coin? So in a good coin, the outcome of one toss of this coin should not influence the subsequent experiments. So if you perform a histogram of such such tosses, so you toss your coin many times in a row and then repeat this pattern, you obtain a histogram. So if we want to set that these tosses or these pulses are statistically independent, the experimental distribution must obey the binomial distribution with the given width. So it happens that it agrees, so we can say that our nanobridge is indeed a good coin in this sense. And coming back to the calibration, to the thermometry, our thermometer is of the second kind, so it needs a calibration. So in order to obtain it, we measure these S-curves for a variety of the temperatures. So we measure, we set a constant bath temperature of, for example, for 100 milli-K, then we change it a little bit to measure another S-curve, another with the different temperatures. And we see that the position of this S-curve that is marked by the probability equals 0.5 is going from the high current to the low when you raise the temperature. And this is a common sense because the higher temperatures contains a bigger amount of thermal energy for the Cooper pairs in the superconductor to be broken, so the switching is easier in the high temperatures. So now by gathering the position of these S-curves, we can obtain a calibration curve like this. So this is what we call switching current mode, because we use current that sets the position of our S-curve to calibrate. So the switching current is a current that produces probability equals 0.5. So we kind of adjust current for a given temperature to give probability equals 0.5. So this is calibration that one can obtain. And now, having that calibration, you can try to measure some thermal transient, and in a given moment of this thermal transient, your system will have a given switching current, so you can invert in some sense this relationship in order to obtain temperature from the measurement of the switching current. For example, if you have for a given moment of your thermal transient, you have 80 microamps of switching current, your system is surely in the temperature of 0.9 Kelvin. So this is first calibration method that is based on switching current, but apart from the temperature dependence of switching current, the probability of the switching is also temperature dependent. So in this case, in the case of measuring temperature using probability, we use constant pulse amplitude. So we choose it and set it and not changing it contrary to the previous mode. We just change the bath temperature. So in the linear regime of the temperature sweep, we observe that the change of the probability due to the change of the temperature is linear. So we can extract slope of such a line and use it as a calibration for the given bath temperature. So to sum up, we change bath temperature and measure change of probability, and this is the basis of the second calibration method. As we see, the second method is much sensitive because it saturates fairly quickly. So the range of the sensitivity here is of the order of tens of millikelvins, whereas here we can trace the temperature gradients from TC basically to to 0.4 K, where our temperatures usually stops being sensitive to the further changes in temperature. And coming back to the issue of the temporal resolution, as I said, the usual time scale or decay rate of the thermal processes in the nanoscale, even in the low temperatures, they are relatively fast. So I drew here two exponential decay with the decay rate of 100 nanoseconds. And we see that even the fastest methods that were previously available in the field is not fast enough to trace nicely exponential decay with such decay rate. So by the time the measurement ends in the bandwidth of 300 nanoseconds, the relaxation is almost finished. So this is not a good measurement. And contrary to this approach, we are able to make our testing pulses very short. So now our bandwidth is limited now by the speed of our generators, but we are surely to be able to produce pulses with duration of the testing of the order of 10 nanoseconds. And we can see that during this 10 nanoseconds, the temperature hardly changes. So this is much better approach to try to trace such temporal profiles. So this is a summary of the first part of the tree, because later I will introduce two experiments that utilizes this switching thermometry we propose. So we have two methods of measuring these thermal gradients. One is based on switching current, and the second one is based on the switching probability. Another thing is that we have this unprecedented temporal resolution that allows us to measure thermal transients that were simply unavailable for the different methods to trace. So the first measurement I would like to present you is the diffusion of the quasi-particles. So now the sample is a little bit more complicated, so I'm going to discuss it. We have three-terminal device made of superconducting aluminum everywhere except here, where you have copper island. Copper is in the normal state in the temperatures of our interest. And the measurement of the diffusion goes as follows. We send some heating current from port 2 to port 1, and this current on its way must go through this normal state island and produce dissipation and quasi-particles because of it. So now, as we produce these quasi-particles, they start to diffuse in all possible directions, and some part of them, at some point, will arrive at the position of our thermometer. And given that they should have still an excess thermal energy by the time they arrive, we should be able to observe at the position of this thermometer an excess temperature. So this is what we try to do. We heat the island, we wait for some time, and then we set this testing that is temperature dependent. And because we rely on the fact that our measurement is of the probabilistic nature, for the given delay between heating and testing, we must perform the same pulse pattern many times. So, for example, the usual value of this patterns in order to obtain the probability is 10,000. So for 1 point, we need to perform 10,000 such pulse patterns. Now, trace of diffusing quasi-particles. On the y-axis, we have counting of the switchings or probability. And on the x-axis, we have delay between heating and testing. So the baseline is chosen to be that way. So in equilibrium, without the presence of additional quasi-particles, we tune the current. So the switching probability is somewhat in the middle of the possible values. So we have we see that at the beginning of the experiment, hardly nothing changes. But at approximately 50 nanoseconds, we see that the diffusing quasi-particle starts to accumulate at the junction. The peak of the presence of these quasi-particles is reached, and after that, the probability comes back to the equilibrium value. So no more quasi-particles in the vicinity of the thermometer at that moment. So we can calculate this probability that was measurement. We can recalculate it to the temperature using this probability mode calibration, where change in the probability with respect to the baseline is proportional to the temperature, to the difference in temperature between equilibrium temperature, bath temperature, and the excess temperature that we measure. So this is how it looks like. This is the measurement of excess electron temperature due to the quasi-particle diffusion in various temperatures. So we see that the amplitude changes, and I will discuss that in a moment why it happens. Nevertheless, we see that the position of the maximum is approximately 300 nanoseconds, and it corresponds to the diffusion constant being of the order of 100 centimeters square per second. So this is the somewhat expected diffusion constant value for the quasi-particle diffusion in the superconductor. This is our technical brag to some extent, because we are able to measure very small thermal effects that are being present in the relatively high temperature. So we are able to obtain below milli-K resolution. So, for example, at this 800 milli-K, the resolution is of the order of 100 microkelvin. So this is quite impressive resolution, I would say. Now to explain to you why the amplitude of this excess heating was changing with the change of the temperature, I need to discuss heat balance equation. So to make it relatively short, we have an area of electrons or quasi-particles that can be subjected to various heat flows and heat outs, actually. So the dynamics of the energy that is here marked by the violet color is given by the all possible heat flows. So we can have Joule heating that is governed by applying some current. We can observe diffusive heat flow and heat flow out from the given volume. And apart from that, electrons inside this area can conduct away heat through phonon channel. So this is just an emission of phonons by the hot electrons. And when it comes to the diffusion, the diffusion itself without the electron phonon now, it is being governed by the diffusion equation with the following solution. This is a Gaussian with the amplitude that is modulated by the time, and x is the distance between source of the excitation and the measure and the point of our interest. So to illustrate what I mean, I draw here two cases. So the first case is what heater sees. So x is equal to 0. So the exponential is equal to 1. We see that at the beginning we observe a high concentration of quasi-particles, and after some time they all left. So this is what we expect from the diffusion. And the thermometer that was placed 60 micrometer far from the source, from the heater, copper heater island in our case, the temporal profile looks like this. At the beginning there is nothing because all quasi-particles are near the copper heater, and at some point they start to appear in the vicinity of the thermometer. So this is free diffusion model without electron phonon coupling yet, because I'm going to involve the electron phonon in the future, and we can check how it matches the experiment. So we can check if the free diffusion model is able to catch the properties of our measurement of the diffusion. And it turns out that if we use this 100 centimeters square per second diffusion constant, it follows that one is able to explain quite nicely the rising edge of this diffusion signal, but after obtaining the maximum, our free electron diffusion model starts to deviate from what we have observed in the experiment. And the reason of this deviation is the same reason that the heating amplitude in the temperature sweep of diffusion profiles changed. So this is electron phonon coupling, and now I'm going to include the electron phonon coupling in the modeling. So we have diffusion channel. Electrons can diffuse through the area of our interest, and they can diffuse away also. But apart from that, we have the thermal link between electrons and phonons. So electrons can emit phonons, and the following differential equation looks like below. We have a diffusion part, temperature dynamics, electron phonon coupling, and Joule heating that actually introduces the quasi-particles. So we must heat for some time before we are able to observe the diffusion. So this is a comparison of the model based on this differential equation, the comparison with the measurements that I have shown previously, and it follows that this model explained the process relatively well. There are some differences for low delays, but mind the fact that here we operate through many orders of magnitude in delay. So this is the reason why we have x-axis in the logarithmic scale. So we have 3 orders of magnitude here that magnifies the discrepancy. So in linear scale, it would not be that much visible. And to summarize the second part, we performed measurement of quasi-particle diffusion, and such measurements were not possible before because of the fastness of this diffusion. So we have obtained quite remarkable agreement between this modeling based on the thermal diffusion equation with electron phonon coupling and the experiment. And the third part is the second experiment. Actually, this is the relaxation of aluminum superconducting nanowire. These results are not yet published. We're going to publish it soon, I hope. Here the pulse pattern is very similar, but now our bridge acts as a heater for some time and acts as a thermometer for different times. So we send heating pulse, and this current pulse is so high that it surely switches the junction. So it creates dissipation, and our junction exceeds critical temperature. And after switching off the heat, the sample starts to cool down. It becomes superconducting again, although now it's overheated. And we can measure the switching probability of the junction in this overheated delays. So again, here, since we rely on the stochasticity of such a measurement, we need to perform many such pulse patterns for a given delay. These are the results of such a cooling from the switching current mode. So we are able to observe the variation in the temperature in the wide temperature range. We see that in low temperature, the relaxation from the temperatures close to TC to the above temperature is relatively slow, of the order of 1 microsecond or even more. But when we go close to TC, this relaxation is much quicker, and time scale here is 100 nanoseconds or even less. So that was switching current mode, and probability mode is here. As I said at the beginning, introducing probability mode, it's much more sensitive to the temperature. So the dynamic temperature range that is able to measure is much smaller, but nevertheless we see here that our relaxation are indeed slow for the low temperature and fast for the high temperature. In here, y-axis is in the log scale, so we see that the measured relaxation traces are indeed of the exponential character, and we are able to obtain the relaxation times from them. We can fit the slopes to obtain the relaxation lifetimes in a function of the temperature. So as I said, the relaxation time is given by heat capacity and thermal conductivity. To account numerically for this relaxation, we also prepared the numerical model based on the heat differential equation that I have shown previously. So these are the relaxation times, temperature dependencies for different lengths of our structure, because the effectiveness of the diffusion will be modulated by this length. If our structures are relatively short, we expect that the relaxation would be quicker, because it could take because the diffusing quasi-particles will need less time in order to leave the structure of our choice. And apart from that, I draw also here the expected relaxation times when I consider electron-phonon coupling only. So this is without quasi-particle diffusion. This is the upper bound, to some extent, theoretical upper bound for the relaxation times values measured in the experiment. And these are the measured relaxation times for the nanowires of the different lengths. We see that longer nanowires, for example, this 800 micrometer, tends to relax much lower than the shorter ones, for example, this 37 or 40 micrometers. I also compared our data with the relaxation times measured in the literature. So they tend to be rather slower, but this can be due to the several things, and the simplest explanation is the fact that they they tend to measure it in the superconducting resonators, and these resonators were decoupled thermally and galvanically from the feed line. So the electrons in this case have no place to go, so they cannot out diffuse from the vicinity of the resonator, from the resonator itself actually. So we tend to measure much faster relaxation times that were not available previously. This is the comparison between the relaxation times modeling and the experiment, and we see that the fan out of the relaxation times models is considerably bigger than we have it for the experimental case. And we are not quite sure why it is so. It is possible that the electron phonon coupling given by the theory is not is not the same as in the experiment. And another thing is that we can have an effect of reabsorption of phonons that were previously emitted by these electrons. Apart from such simple experiments, we can have something a little bit more sophisticated to some extent, because we can send one heating pulse prior to testing, but we can send many of them, so 600 heatings before one testing. And in this case, we observe two relaxation times actually. So the first relaxation time, as in the case of the single heating, is the electron phonon relaxation time with the diffusion. But these electrons tend to relax not to the bath temperature, but to the overheated phonon temperature, because the large amount of heating pulses tend to heat up the local phonons, and this local phonons acts as a reservoir to some extent to these electrons, and by the time these electrons equilibrate temperature with these phonons, then they can go together to the bath temperature of the sample holder. So this is summary of the third part. We obtained qualitatively agreement of our experiment with proposed relaxation model that consists electron phonon coupling with the diffusion. We observe a rather weak length dependent relaxation, at least not so strong that we expect from the model. And basing on two thermometry methods that we have, switching current method and probability method, we can measure the thermal processes in wide temperature range. This is the switching current method, and we can investigate also small temperature excesses, which is a property of a probability mode. We would like to express gratitude to our fundings. We've got first team grant, and now we have Sonata Bis. And I would like at the end to advertise our site that is quite new. You can find all of our publications there, informations about our team, presentations and posters are also there. And most of our presentations are also available at our YouTube channel. So this is youtube.com/@coolphonegroup, because we are dealing with cool phonons mostly. So this is the name of our group. This is the bibliography. If you are interested in foundations of switching thermometry, this is our earliest paper. Correlation studies that deals with the coin flip character of our junctions are presented in these two correlation studies paper, and the diffusion experiment were published in Physical Review Applied as well. You can find it. As I said, the quasi-particle relaxation experiment is yet to be published. So this is everything I have for today. Thank you, and I'm waiting for your questions.
All right, thank you very much for your presentation. So, do we have questions in regards to given presentation? Maybe I will have a couple of questions. Can you monitor the state of superconducting qubits using the thermometer which you have constructed? And
Well,
yeah,
I suppose yes. I mean, this is the problem of the temperature that is being used in the superconducting qubits, because I assume that they measure it in tens of microkelvins probably. So our thermometer is sensitive from 400 millik. So in this case, not. But if you change the superconducting material to some that has lower TC, you will surely can do it. Here. So we are starting to be sensitive at 300, 400 millik. But this is the case of the aluminum. If you change TC, if you change the TC of your material, you can obtain sensitivity at the lower temperatures.
yeah, yes, thank you. So I have also remarked, so your thermometer bases on quasi-particles, right?
Yes.
So it means that if you approach absolute zero temperature, you have almost no quasi-particles present, right?
Yes. So this is the reason why in low temperature there is no sensitivity.
Yeah. So let's say, so what's the lowest temperature you can measure by this thermometer? Do you see any practical number that you can come out?
The lowest temperature that we can measure.
Yeah, like 10 millikelvin. Can you still grasp effects at 10 millikelvin?
Well, the lowest practical temperature that we can measure to use that we can measure is like 250 millik, I believe, because at this temperature probability mode, which is much sensitive to the changes in the temperature, produces some residual sensitivity, I would say, but I wouldn't go lower than 300 millik.
I see. Okay, because it's just a question. So, for example, how to measure temperature at very low values? So, shall we use single electron devices, semiconductor single electron devices? You are using Josephson, kind of Josephson devices, right?
Yes. This nanobridge is Josephson junction to some extent.
All right, and I'm just curious. Is your group capable of going towards superconducting qubits?
Yes, I think so, but we have many other investigations now. So we are a relatively small group because we have 2 PhD students and 2 doctors. So there is not enough of us to pursue all the directions that we have. So, for example, now we are working heavily towards measurements in the magnetic field that is considering vortices and their influence on this thermometry. So such a vortex can influence the heat flux of these quasi-particles, because this vortex can act as a quasi-particle trap. Inside this vortex, quasi-particles behaves like normal electrons, so they relax much faster.
I see. And did you manage to do you see some commercial potential of your solutions? Do you imagine that your thermometers can be widely spread across worldwide?
Okay, so here the issue is that we rely on the stochasticity. So we, for every point, you need to perform a lot of measurements. So we like to brag that we have nanosecond resolution, but the fact is that the measurement of the single delay point lasts like 2 seconds or so. So I assume you would need to have quite modular system with the generator, junction, and voltage drop readout all inside some small device. So I would say actually I don't know if that would be beneficial to place everything in you know the mixing plate of the dilution refrigerator or something like that. We mainly focus on the basic physics here.
I see. So you have research motivation driven by fundamental research.
Yes, we are strongly fundamentally oriented here.
I see.
Although we like to publish in Physical Review Applied, and they like us, I think so. This is to some extent applied physics as well.
Okay, thank you for the answer. So do we have any more questions from the audience, from Zoom audience? If not, thank you, the speaker again.
Thank you.